And we'll go from current slide.
All right. Before we get started, a couple of things, just sort of minor announcement type things, but could have some bearing. Depends on where you happen to be in your progress and stuff. Number one, if any of you are in a mini-term course, first mini-term course, you're probably already quite well aware that either yesterday or today was the last day of class, okay? Which also means, hopefully you're aware of this as well, that you student course evaluations for the mini-term classes, not for these full-term classes. Mini-term classes, they are open. So if you are in a mini-term class, please do your student course evaluations. I value them for myself. I also value them as an department chair because I can arrange to go observe an instructor, and that instructor can put on a really good show that day, and I think that's how he or she teaches every day, but I may be wrong. The student course evaluation lets me know what the students really think over the course of the whole term, and so it's usually a lot better source for my evaluation of those instructors because I'm a department chair. Okay, so please do your student course evaluations. Now, the other thing to do with that, since the mini-term one is just ending, that means we're really close, as in midnight tonight will be midterm, okay? Before that first half of the term, after this, the second half of the term. And sometime after midterm, usually within a few days or at least a week, they usually ask us to do midterm progress reports. Okay, what that means, any student who has a D or an F at midterm, we're required to let people know that. Okay, now this class, of course, one of my best classes ever, I've gotten 3 research papers in. Thank you for getting those in, but that's a pretty small number for this bigger and greater crowd. The first test, I've got all but 1, 2, 3, 4 in, which is good. 2, and here we have Caitlin and 3. All right. So, if one of you 4 who has not turned in the first test has also not done a research paper, turned in a research paper, I have 0 grade for you. And guess what score that goes down for grade at midterm? Not a good one. Okay. So please get me something by the end of this week. Either your research paper, your first test, or your second test. Get me some score. I've given most of you the second test already. I did. Oh, I thought I did last time. Okay, I'll be giving that today. Huh?
I have it.
Okay, a few of you did. I think you had to leave early, maybe. Yeah, but I mean, it's not. I wasn't going to give it till today, but I had it run off, so those who asked for it got it. Okay, so anyway, you can get something into me by the end of the week, so I don't have to put down a score that's not going to be representative of what you've been doing. Okay. And by the way, these midterm progress reports don't really mean anything. They don't hurt your score or anything else. What it may mean, though, is you might start getting bugged by people. Anyway, you can provide tutoring, or do you need counseling, or do you need help with this? And if you don't want to be bugged, get something into me so you won't be bugged. Okay. Now, the one other issue, I say get it into me by the end of the week. However, I will not be here on Friday, which is the end of the week this week. I have meetings down in Mobile that I have to leave home around 7 in the morning to drive 4 to 5 hours to get to Mobile, and then attend a 3-hour meeting, and then turn around and drive 4 to 5 hours back. So 8 to 10 hours of driving to do a 3-hour meeting. It just doesn't seem quite right to me, but they said I had to go. So anyway, I will not be on either campus this Friday at all. Now, next Friday, I will be here on this campus at the very beginning, but not for very long, because I have an eye appointment right across the road here at UAB West, okay? And then, after that eye appointment's over with, I'll probably be heading toward the Birmingham West campus. So I will be out of pocket for maybe the first hour of the morning, maybe a little more. It depends on how long it takes. We'll see. Okay. And that was, yeah. Finding you, though, is hard.
Oh.
Yeah, Ariel. Right. Okay. All right, good deal. And now I got Demetrius. I think I got everybody else who came in. Okay. Now, so please, so don't look for me this Friday, but next Friday, don't look for me early because I'll be at the doctor. And I don't know what time they'll finish, but I'll get to the Birmingham West Campus as soon as I can after that. All right. Any questions? Anything we've done? Any other issues? All right. So we're in finishing Chapter 4, Trigonometry. And 4.8 is Applications and Models. And here's another application of trigonometry. Harmonic motion. Now, when you hear either of those words, what comes to mind? Harmonic. I think music, okay? But this doesn't have to. It does relate to music, but it doesn't have to be relating to music. When you put the motion in there, that sort of takes it away from the music, but it's still there, okay? And what this means is what a harmony is, Seth can probably fill me in on this some, that's when you have notes that really go well together, okay? Which generally means there's something in common with their frequencies and their wavelengths and those kinds of things. Whether musicians know that's what they're doing or not, that's what it is. So you're talking about motion here. You're talking about vibration. You're talking about rarefaction and condensation. You're talking about all sorts of things. But any kind of periodic motion is harmonic motion. Periodic, that's what sines and cosines are. So sines and cosines are very well adapted to modeling harmonic motion. The periodic nature of the trigonometric functions is useful for describing the motion of a point on an object that vibrates, oscillates, rotates, or is moved by wave motion. Okay? For instance, Earth going around the sun. Very periodic. We do it once a year. Okay? Or spinning on our axis. We do it once every 24 hours. Okay? Moon going around. Lots of things in nature are very periodic. Night, day, amount hours of daylight, darkness, all kinds of stuff like that. Even temperatures, on average, are very periodic. Okay? And all these things can be modeled and viewed using sines and cosines. Okay? Here's one other, a spring. So let's say we have a ball hanging on a spring here. Okay? Now, if it's just hanging there at rest, it's at its equilibrium position. It's very happy right there, just hanging there. Okay? However, if you were to take the ball and stretch it down here, the spring is not so happy anymore. It's trying to pull back on you by Hooke's law. Okay? The string is trying to pull back to return it to that original position. So if you were to release it from here, when you first release, your velocity is zero because you've been holding it very steady. But as soon as you release it, it starts picking up velocity, trying to return to its equilibrium position, and the spring is pulling it the whole way, so it's accelerating it, so it's going faster and faster until it gets here, but now it's at its maximum speed. So it's going to overshoot it, for sure, and compress the spring and go up here, okay? But as soon as it starts compressing the spring's not happy again. It starts pushing against it, slowing it down as it's coming up there, finally making it stop, and now it's going to push back. And then it repeats the process, goes back here at its maximum speed, overshoots, slows down until it gets to its maximum displacement, starts being pulled back, and just goes up and down and up and down and up and down. Now, it won't do that forever because springs are not perfect. They have friction, internal friction. They may heat up a little bit, meaning you've lost some energy there, but it will do that for quite a while. If you've ever been ridden in a vehicle whose shock absorbers were not working well, and you hit a pothole, you know you'll do that for a while down the road. Maybe y'all have never traveled in vehicles like that, but it has happened. Okay, and lo and behold, rhymes here. Okay. All right. Good deal. So this is going to be an example of periodic motion. Guess what? When you pull it down here, it's at its maximum length. Okay, actually minimum length, the way they're measuring it here. I'd say maximum stretch, but they're saying minimum height above the ground. So this would be a reflected cosine function. You start down here and then it starts moving from there. Perfect. If it started here and you happen to throw it down somehow so that it reached here and stuff, that would be exactly the opposite of the sine function, because it's going down to begin with or up, but it's starting at the equilibrium position. If it started up there, that would be a perfect cosine function, because if you compress it, get it up there, then release it, then it starts its motion. So any one of those can be represented by some type of a trig function, sine or cosine. All right. Suppose that oh, let's go back to that. What would this 10 centimeters either down here or up here represent? The word we've used before. A word. One of the amplitude. Very good. That would be the amplitude. Okay? And that's about all we can do with that right now, so let's go back here. Suppose that 10 centimeters is the maximum distance the ball moves either vertically upward or downward from the equilibrium or rest position. That would be the amplitude. Suppose further that the time it takes, what would be related to the time in our parameters if we were modeling this with a trig function? Time is related to, second? Okay. To the trig function. The parameters of the trig function. Time is the period. Okay? Suppose further the time it takes for the ball to move from its maximum displacement above zero to its maximum displacement below zero and back again is 4 seconds. You've just defined its period. Ah, Cody's here. Just in the nickel dime. Okay. All right. So that would be your period. The time it takes for it to move from one position back to the same position going in the same direction. There's your period. And that's related to which of your letters in the trig function? Period is related to the B. Okay? Assuming ideal conditions of perfect elasticities, no internal friction in your spring, no air resistance, okay, no friction, no air resistance, the ball will continue to move up and down and up and down and up and down and up and down, and you get as bored of that as you would of me. Never mind. Okay, so that gives you periodic motion. From this spring, you can conclude that the period, or time for a complete cycle, is 4 seconds. Okay? That right there tells you the first part of how you can write a trig function to represent this motion. What do we call period? Well, we call it period. But what was the formula that went with it? B. Okay, D had to do with it. How is B related to the period? Okay, since we're doing sine or cosine, 2 pi divided by 4, that's your period. So we have pi halves would be your B, right? There it is, okay. Amplitude, 10 centimeters, so you have the A, little a is 10. The frequency, now we haven't mentioned that before, I don't think. What frequency is, okay, now think of this. The period is how long it takes to do one cycle, okay? That's the period. Frequency is how many cycles you get in one period, okay? Or not one period, in a given period, like in per second or per minute. So in other words, frequency and period are inverse of each other. They're reciprocals of each other. This is time per cycle. This is cycles per time. So it's just a reciprocal of that. Okay? Motion of this nature can be described by a sine or a cosine function and is called simple harmonic motion. Okay? Introducing the new concept of frequency here, which is a very simple thing, 1 over the period. So, definition of simple harmonic motion. A point that moves on a coordinate line, either up or down or right or left, okay, is in simple harmonic motion when the distance d from the origin at any time t can be given either as a sine function or a cosine function. Now those look fairly familiar with, except for one possible, well, 2 deviations from what we've done before. One was, we usually call d the vertical displacement. That's not what, let's see, is that what we're talking? No, usually we just said x or y or something else like this. This is now your dependent variable. Okay. What's the other? The a was just like the a we've seen before. What's different here? Anyone even know what this is? One thing it's not a w, no matter how much it may look like a w. That is the lowercase Greek letter omega. Okay? Looks nothing like the uppercase omega. Uppercase omega looks like, ooh, let me get my pen. Uppercase omega looks like that. Looks nothing like that. This is lowercase omega, and that stands for, and we usually think of it in these contexts as being angular frequency, but really, and that's exactly what it is, the angular frequency, but it's just like the B we were talking about before. We didn't give that a specific name, but now this omega, it's just like the B before, where A and omega are any 2 real numbers, omega always positive. We don't have it 0 and we don't have it negative. The motion has amplitude, absolute value of A, and the period, just like before, 2 pi over B before, omega now. Same place, same thing. Frequency would then be the reciprocal of that, omega over 2 pi. So the frequency is omega divided by 2 pi. The angular frequency, without the 2 pi in it, that would be omega. The book doesn't call it that, but in physics you'll run into that. Okay. Now, so now they say, this is example 6 here. Yeah. Page 332. Write an equation for the simple harmonic motion of the ball described earlier by this figure, where the period is 4 seconds, just like before, and it says what's the frequency of this harmonic motion. Okay? So, first it says write down an equation. So what would the equation be? If we're starting from here, they don't say that we are. If we are starting from here, which trig function would you use? I would use the sine because it's starting at the equilibrium position. If we're starting either of the other 2, I would use cosine. So let's use, and they use the symbol D, okay, which means the distance from equilibrium, by the way. What would that be then? What would be your equation?
10 at the period.
I'm sorry?
10 the period.
10 centimeters, is that what you said?
10 the period.
10 what?
10 centimeters.
Yeah, okay. Yeah, that would be the amplitude, not period. Yeah, the period is they just said here, period is 4 seconds. This is 10 centimeters. So I'm going to put 10 centimeters in. I'm also going to put negative. Why am I going to put negative?
Because you're dropping it.
It's going down first. That's how it appears. Now, if you're thumping it up first, that would be a positive, okay? That would be going up this way. But it appears you're thumping it down here, so it's going down there. It hurts my finger to do it. But anyway, we're going to assume that. So minus 10 centimeters, and we decided on the sine function, didn't we? And then what would go next? We might need to do a little figuring here, though we have already done it.
informally, but let's do it here. The period is 4 seconds. The period, 4 seconds. And what is period? Y'all gave it to me before.
Oh, 2 pi over
Omega. We used to say B, now we're going to call it omega in the context of simple harmonic motion. So we need to get, oh, I guess we ought to do this too. What is our standard form for the sine model? D is equal to A sine, help me somebody, omega t. Okay, where omega is this thing we've got here. So let's solve this for omega, which will be multiply both sides by omega and divide both sides by 4. Omegas go out on this side, and you have 4's go out on this side. So you have omega is equal to what? Pi halves. Okay. Now that really has units. It's in per seconds because the 2 pi has no units, but the 4 that we divided by do. So that is in a per second. So omega is pi halves. So sine pi halves t. There we have it. Okay. A is the absolute value of A is your amplitude. We already decided that was going to be 10. But because we're going down from the equilibrium position, I'm going to say minus 10 centimeters times sine of pi halves t. Okay? Now, second question it asks for is what is the frequency of that harmonic motion? You don't need any of this for that. They're going to come back and use it, but we know frequency is what? Anybody? 1 over the period. Right? Okay. Now, let me go and give you this. Quite often when we're dealing with simple harmonic motion in physics, the symbol for the period is going to be capital T, which is a little unfortunate because capital T in physics usually stands for temperature, okay, usually in Kelvin. This is not temperature, this is the period. So frequency is 1 over period, and what was our period? 4 seconds. So this is 1/4. And that would be cycles per second. Now, since cycles isn't really a term, isn't a unit of anything, we'll quite often say 1/4 per second or second to the minus 1. Means the same thing. There is actually a unit that is a per second. Does anyone happen to know what that is? A hertz. You've probably heard of something being so many kilohertz or megahertz or hertz or whatever. That was looking more like a 9 than it was a 4. So it's 1/4 of a hertz. Okay. Usually we don't use hertz for this small a frequency, but you could. Okay, or per seconds. Actually, it's cycles per second. Sometimes you'll see CPS, that stands for cycles per second. All right, that's what we got. Let's see what they got. Any questions on this before we move on? Okay. Because the spring is at equilibrium, D is equal to 0. When T is equal to 0, let's use the sine. So D is equal to A sine omega T. That's our basic formula for simple harmonic motion. Or it could be cosine, but we're using sine because it was at equilibrium to begin with. Moreover, because maximum displacement from 0 is 10, and the period is 4, we have the following. Amplitude is absolute value of A, which is 10. The amplitude is 10. Period is 2 pi over omega, and that is 4, we know, so omega is pi halves, just like we got. And consequently, the equation of motion. Now, that's exactly what we have, except they left off the minus sign. Obviously, theirs was going up first, even though the picture showed it going down first. But it really doesn't matter. That is the equation of motion. I prefer it with the minus 10. Notice that the choice of A equal 10 or minus 10 depends on whether the ball initially moves up or initially moves down. The picture showed it moving down, so I went with minus 10. They, however, obviously thought it was going up first, which is easier to thump up than thump down, I think. The frequency is 2 pi, omega over 2 pi, which to me is going around your elbow to get to your ear. We already know the frequency is 1 over the period, but doing the way they did, their omega was pi halves, divide that by 2 pi, and you get 1 over 4 cycles per second, which, if you had just taken the formula I gave you, frequency equal 1 over period, you had that just by writing it down. Okay, so let me get Jake here. Good attendance today so far. Corinthia we're missing. And Devin. And those are the only two we're missing, I think. Way to go, team. All right. Any questions? This was example 6 on page 332 in chapter 4, trigonometry, 4.8, applications and models. And after every example, there is, of course, a checkpoint. Good idea to do those soon after class. Okay. All right. Another illustration, or one illustration of the relationship between sine waves and harmonic motion is the wave motion that results when a stone is dropped in a calm pool of water. And you've seen the ripples go out, the waves go out from there. Waves move outward in roughly the shape of a sine or cosine wave. If you pictured drawing the surface of the water, so it's going up and down and up and down. Sine or cosine wave. This one starting with up here, I would say a cosine wave, because it would find real max. Okay? Either one. As an example, suppose you're fishing, and your fishing bobber is attached so it does not move horizontally. In other words, you got a pretty good weight on it, lead weight on it. So, but it doesn't move horizontally, but it goes up and down when the stick jet ski goes by, and it disturbs all the fish and stuff. It leaves a big wake and stuff. The bobber will just start moving up and down. The waves move outward from the drop stone. Okay, it isn't a jet ski. Okay, your fishing bobber will move up and down in simple harmonic motion. Now, this figure, I know what they're trying to do. I don't find it particularly emotionally gratifying. I mean, it looks so confusing, but what they're saying is at one point your bobber is right there, and then it would be on that part of the sine curve, because it can't move side to side. Then it's going up here, it would be on that sine curve. Up here, it would be on this one. But if it dropped down here, it would be on this one or on this one. So I sort of see why they draw it, but I don't really get any warm and fuzzies out of looking at that picture. I don't. Suddenly, everything doesn't make perfect sense to me. I have to think, okay, this is what they say. Here's initial time, it's down here. The next time, a little bit later, it's moved to this one, and then it moves to this one. Yeah, so that's why the bobber moves out. Okay. Stone was dropped over here. Any questions? Again, I don't find that a really revealing figure. Maybe you do. All right. There is at least one more problem here, and this is example 7. Yeah, this is the last one. So let's go back to some place that we can write, like right here. Consider the equation for simple harmonic motion. D is equal to 6 times the cosine of 3/4 pi t. And find A, okay. Consider the equation. Find A, the maximum displacement. Anyone do that right off the top? 6. Very good. We don't know 6 what. They don't tell us what your unit is, but maximum displacement is 6. Okay? B, because that's the absolute value of the amplitude of A. It is the amplitude. Okay. B, the frequency. Can anyone right off the top tell me the frequency? Okay. It's this B, which you have here. The B here is, or omega here, is 3 pi over 4. So the period is 2 pi over that B, which is 3 pi. Can I write the 4 up top rather than writing it in the denominator? And again, that 4 looks more like a 9. I'm having trouble with my 4s today. Rather than writing the denominator in the denominator, let's just move it upstairs to be there. Okay? So what does this give you the period to be? Anybody? 8/3? Looks like that to me. So the frequency is 8/3. I'm going to put CPS, cycles per second. We don't know that we're dealing with seconds. They didn't tell us that, so I'm just going to make that assumption. 8/3 cycles per second. Okay? It's cycles per unit time, the way they say it. Okay, good for them. Okay, the C part then. C part says the value of D when T is equal to 4. What is D?
Wait, isn't the frequency the reciprocal period?
I thought, oh wait, you're right. Right. Okay, I'm sorry. This is the period, so frequency would be what? 3/8. Thank you. And that would be, and by the way, I had the terms wrong. This would be seconds, or time periods, okay, whatever that is, and this would be cycles per second. Okay, thank you. Good catch there. 3/8 of a cycle per second. Okay, good deal. Now number C is asking about D, the value of D when T is equal to 4. So I'm going to write this, this may look a little strange. D is a function of T, because that's really what you're dealing with here. And this would be, here is your function, 6 cosine 3 pi over 4 times the T here. Okay, that would be T. Okay, and we're looking for D when time is equal to 4. So this would be 6 cosine 3 pi over 4 times 4. They don't say 4 what, okay? They just say when T is equal to 4. Seconds or whatever it happens to be. Can anyone make that calculation for me? Pretty easy to divide out the 4s, right? And what's cosine of 3 pi? Calculator slow you down. Okay. What do you say? Okay, it's the cosine of 3 pi is -1, because cosine is here, pi is -1, 2 pi is +1, 3 pi is -1. So it'd be 6 times -1, -6. Whatever units you have, they haven't told us what these are. I'm going to guess centimeters, but it may have been something else. So there's the C part. Let's see if we can get the D part done. The least positive value of T for which D is equal to 0. The least positive value for T of T for which D is equal to 0. Okay, so here's our equation, and we want to say 0 is equal to 6 cosine 3/4 pi times t, and we're looking for the smallest positive value for t, which would make that sentence true. Did you finish?
Yes, sir.
Is she still working on hers?
I thought she came to turn it in. Because she left the water back
Okay. She hasn't been by here.
there. Was it about Mina?
Yeah.
Do you want me to call her?
Yeah, just find out what she did with it. She may have slid it under my office door, which is fine.
Probably. I'll
Okay.
call her.
Okay. But if she didn't, I need to know where it is because I need it. Thank you.
Yes, sir.
Sorry about that. Okay. So, we need the smallest value of t, positive value of t, that will make that sentence true. How could we proceed? Anybody? First thing I want to do is divide away the 6. Is that legal? Sure. Okay. So now we have, you got rid of the 6 here, and that's still 0. So you have cosine of 3/4 pi t is equal to 0. Everybody agree? Now, what we want is the smallest positive value for t, which will make that true. So basically that means the smallest value of this thing for which cosine is 0. What's the first 0 you get to with the cosine?
0.
No, cosine starts at 1.
Cosine.
Sine starts at 0. Cosine starts at 1. What's the first 0 you get to?
Y equals 1.
It's what?
Y equals 1. So I'm going to.
Y is equal to 0.
Oh, I'm saying, but if you.
Okay, but what is the x value or the t value that first 0 you get to? This cosine's coming down. Which? Let's see.
You said 5 or 2.
Well, then why didn't he say it? Okay, 5 or 2. So that value of that is equal to pi over 2.
She put it under your office door.
Fantastic. Thank you so much. So what we have here is that 3 pi over 4t is equal to pi over 2. You see, that's the first, okay, first value that you would get to where cosine is equal to 0. So solve that for t. Say again? Okay, if you divide out the pi's, multiply by 2, divide by 3, multiply by 2, divide by 3, and you have, looks like to me, 1/3, doesn't it? Oh, no, I multiplied by 4, sorry. Multiply by 4 and divide, so that would be, you said 2/3? Is that what you had said? Okay. I think it's t equal 2/3. I can't write today. T is equal to 2/3. Because what we had here, this thing in here, the first 0 you get, positive 0 you get, is when this thing in here is equal to pi halves, like you said. That's the first 0 you read from the cosine function. So 3/4 t, 3 pi over 4 t is equal to pi halves. Divide out the pi's, divide by 3, multiply by 4, and that gives you a 2 up here, 2/3. Okay?
Okay, hold on.
Got it?
Re-explain it.
Okay. My writing has just been awful. Okay. Now, this statement right here. Okay, we know cosine starts at its max here. Okay? The first 0 it gets to is when the entity you're taking the cosine of is pi halves. Right. So therefore that entity is 3 pi over 4t. But that thing is pi halves. So 3 pi over 4t is equal to pi halves. My pen is so slow. There's your equation. Okay. Now, we want to isolate the t, get a naked t by itself there. So let's multiply everything by 4. Okay? That'll wipe out the denominators here, and that gives you 2 here. So you got 3 pi times t is equal to 2 pi. Divide everything by 3 pi. Okay? this all goes, the pi's go, that's sad, isn't it? And t is equal to 2/3. 2/3 of a second or whatever your units are. 2/3 time units, okay. And I think that's what they got here too, so the least value is 2/3. All right. Now, yes? B. All right. What B was asking for was, what is the frequency with, okay. I'm going to erase a bunch of this stuff because anyone have questions on any of the others I need to leave up here? No. So let me erase everything except B. Okay? Including what we just did. In fact, including that ugly mess. Okay? So it just gives us more room to work. All right. Goodness gracious, my eraser is so slow. Oh, it's picking up a little bit now. I guess I'm getting more things off the screen. Okay. One of these days we'll be through. Here we go. All right. And we even erase this. Okay. What we're looking for is frequency. Given this. Okay? Well, this is what we call our omega, right? Which is the same as the old B. What we used to call B, we now call omega in simple harmonic motion. And how is, okay, we didn't used to mess anything with frequency. What we messed with was, what is related to B? Second. What's related to B? Sine is equal to, or A cosine BT, what was related to the B? The period, okay? And what is the period? The period is equal to, for sine or cosine, this is cosine, 2 pi over B, which in this case is 2 pi over our omega, which in this case is 2 pi over 3/4 pi. So you could write this 3 pi over 4. Now that's awkward, so I want to rewrite that as 2 pi divided by 3 pi over 4, which is 2 pi, how do you do division of fractional forms? Yeah, multiply by the inverse, 4 over 3 pi. Okay. So at this state, we can divide out the pi's, and that leaves us with 8 over 3. 2 times 4 over 3. That's the period. The frequency, we know, is 1 over the period. Or I was using capital T because that's what you'll use in physics. So this will be the reciprocal of that, which is 8. Doing it again. 3 over 8. Just reciprocate the 8/3 and you get 3/8.
So you would always put the period over B, and instead now you're putting the period over omega.
And yeah, if you wanted to start and do frequency, that would be a great way to do. Since you know it's the reciprocal of that, frequency is equal to omega over 2 pi. A great way to go. And here your omega was 3 pi over 4 divided by 2 pi. Well, the pi's obviously go out. You can divide by 2, and 3/4 divided by 2 is 3/8. So you can get there directly that way. That's another very good way to do it. Is adjust your formula to begin with, rather than doing 1 over P, just invert that and say it's omega over 2 pi. And that would be cycles per second typically. or whatever, cycles per unit time. All right, good questions. Any others? There is a checkpoint. Try to do that as soon as you can. It's answering the same 4 questions, but now you have a different motion formula. Okay, homework. Well, before we get to homework, vocabulary. A blank measures the acute angle that a path or a line of sight makes with a fixed north-south line. Think navigation or surveying. A blank measures the acute angle that a path or line of sight makes from a fixed north-south line. Bearing, exactly. Number 2, a point that moves on a coordinate line in simple blank blank, when its distance d is from the origin at a time t is given either by a sine or a cosine function. Simple blank blank. Harmonic motion, very good. Number 3, the time for one complete cycle of a point in simple harmonic motion is its blank, period, and the number of cycles per second of a point in simple harmonic motion is its blank. Frequency, very good. All right. Homework exercises, do any of the odds, 5 through 11. They're all at Calc Chat, 9's at Calc View. Do either 13 or 15 or both. They're both at Calc Chat, 15's at Calc View. Then do any of the odds, 17 through 23. Those are all length or distance or height problems. They should all be at Calc Chat. Then do either 25 or 27. Those are angle of elevation or depression problems. Then you got some more heights or altitude, 29. And all these should be at Calc Chat. Then we had that speed enforcement problem. We had one sort of like that in the text at 31. And then we had some of our relative bearings at any of the odds 33 through 39, say. And then we had some general geometry problems, 41 or 43. All these should be at Calc Chat. And then the simple harmonic motion problems, we had either 45 or 47. They should both be at Calc Chat. Then, more musically inclined, the tuning fork problem is 49. 2 more simple harmonic motion, 51 or 53. They all should be at Calc Chat. And then we have some other applications of simple harmonic motion, 55 and or 57. They both should be at Calc Chat. Then you have true false, number 59. And that's it for this one. There is a chapter summary, which might be good for reference for formulas and equations. And then there's review exercises. So if you need any additional homework exercises, the first 4 sections were the first test. If you don't have that turned in yet, you might find additional help here. Odd numbers are in the back of the, I think all the answers are in the back of the book. The only odds are at calcchat.com. But then the second test, which if you didn't get it already, you'll be getting today, it'll be 4-5 through 4-8. So you could do any of the odds 63 to 67. They're all at Calc Chat. 69 should be at Calc Chat. And 4.6, 71 or 73 are at Calc Chat. And 75 should be at Calc Chat. And 4.7, either 77 or 79 should be at Calc Chat. 81 or 83 should be at Calc Chat. 85 should be at Calc Chat. Either 87 or 89 should be at Calc Chat. And 91, I don't know if that's a Calc Chat or not. You can look it up to see. And then the last section, 4.8, 93 or 95, they should both be at Calc Chat. There's a true-false, 97, that should be at Calc Chat. Something alrighty, if you want to do that, and then that's either 99 or 101. I'm not sure they'll be at Calc Chat. Then, if you haven't had enough, the chapter test. And again, I know all these answers are in the back of the book, even and odds, but at CalChat it's still the odd number exercises. So you can do either even or odds or both or whatever. 1 through 7 should be at CalChat. 9 should be at CalChat. 11 or 13 should be at CalChat. 15 should be at CalChat. And any of the odds, 17 or 19 at CalChat. Okay. A little proof on Pythagorean theorem. Sort of a fun one. There's several hundreds or thousand proofs out there. This is just one of them. There's a problem-solving problem there. You can look at that. Interesting one if you're going into optics and physics. There's a good one. I see a picture there. Next is analytical trigonometry, chapter 5. That's what we'll be going to next. But before I forget it or anyone leaves, let me make sure all of you have the second test. And I need the first test in forthwith, or sooner, if you got it. Okay. All right, I'm getting close. All right, here we are. And I'll also ask you if you need graph paper, because this one, if you may remember, sections 4, 5, and 4, 6, I think were both graphing. So this has quite a bit of graphing on it. Okay. Who did get the second test?
I got mine.
You got it. You got it. You got it. You need graph paper? Okay. Now, this graph paper is printed in front and back. If you can get 4 on one side and 5 on the other side, if you need more, I got more graph paper. Okay? You got it. You got it. Right? You get it. You got it. Okay. Oh, good. It's fine. Even deal. Okay. So you need graph paper? Okay. You got it. Okay. You graph paper?
For number 2, what's the vocabulary?
You graph paper? Graph paper?
Bigger.
Number 2? I got it.
No. Number 2 is harmonic motion. Harmonic motion.
You graph paper? If you need more, I can certainly do it. You graph paper? Huh?
Very nice, cute little that half.
All right. One person we're missing. That's got the test. I'm guessing that's either.
Does that
All right. So please, folks, get me your first test and or your research paper, if possible, before Friday. By next class, if you can. One or the other, but so either Corinthia or Devin. And we may have actually lost somebody because, okay. So maybe we won't need those. Okay. Any questions? All right. How are we doing on time? I haven't got my watch out yet. Oh, we got 10 minutes, don't we? Huh?
Oh, it's not 11.
Okay. What do we go till?
11:03.
Yeah. Okay. All right. So let's now go to 5.1. Yeah, 11:04. So we got more than 10 minutes. 11 minutes. All right. Now, what in the world could we possibly be meaning by analytic trigonometry? Any ideas? Usually to analyze means to work through something. Most of the first chapter was just introduction to trig, drawing trig graphs, solving some problems with it. Now we're going to be sort of manipulating trig entities. So, one of the things we're going to start with using our fundamental identities. In fact, that's what we're going to use for in our manipulations pretty much. So we'll first need to recognize and write the fundamental trig identities. Now, if you recall, we had these when we dealt with the unit circles. We had it when we went to angles and triangles. We had them when we went to, seems like one or two other times. We're going to deal with them again. So you might get the idea these trig identities are sort of important, okay? We've had them repeatedly. Anytime something's repeated many times, usually means it's pretty important. We use those that have fundamental trig identities there to evaluate trig functions, simplifying trig expressions, and rewriting trig expressions, okay? So here's the introduction. We will learn how to use the fundamental identities. They love these things, don't they? To do the following. Evaluate trig functions, simplify trig expressions, develop additional trig identities, and solve trigonometric equations. Almost the same thing we saw on the last slide. Here they are again. As if you haven't seen them before, here they are again. The reciprocal identities, what is sine? 1 over cosecant. What is cosecant? 1 over sine. Cosine is 1 over secant, and secant is 1 over cosine. Tangent is 1 over cotangent, and cotangent is 1 over tangent. Your quotient identities, what is tangent? Second? Sine over cosine, and cotangent would be?
Cosine over sine.
Cosine over sine, because it's reciprocal, right? Okay, Pythagorean identities. Oh boy. What's the most famous of these? The easiest, handiest. Use a lot. It's similar to that. That's Pythagorean theorem. Except now, if you think of a squared being the cosine squared plus y squared being the sine squared, that's the b squared, and this would be, especially if you're on a unit circle, 1. Sine squared plus cosine squared equal 1. No matter what the angle is, no matter what the u is, the sine squared plus the cosine squared is always, forever, equal to 1. The sum of those two. Now, if you took this one and divided everything on both sides by cosine squared, what would this be? Sine squared divided by cosine squared is? Tangent squared. Cosine squared divided by cosine squared is?
Cotangent.
Cosine divided by cosine is? 1, okay? And 1 divided by cosine squared is? Secant squared. So 1 plus tangent squared is secant squared. They got the order out, but it's fine. And if you took this and divided everything by sine squared, that'd be 1 plus cotangent squared is equal to cosecant squared. Perfect. All right. Now, the cofunction identities. I don't use these nearly as much, but they make sense just from what they are. The sine of the complement of an angle, which is exactly what this is, pi halves minus u would be the complement of u, right? Because the complement of two angles are complementary if they add up to pi halves, or 90, right? So therefore you subtract 1 from 90, or pi halves, and it would be the complement of the other. So the sine of the complement is equal to cosine of that angle. Okay, the complement. Sine of the complement of u is the cosine of u. Think of the co as meaning complement of the sine of u. Okay.
The u can be anything. Use a variable, right?
Use the variable, exactly. So whatever your angle was, u, the sine of the complement of u is the same as the cosine, the complementary sine of u. That's what that means. The cosine of a complement would be the sine of u. The tangent of a complement is the cotangent. The cotangent of a complement is the tangent. The secant of a complement is the cosecant. See, the co means complement, okay? And the cosecant of a complement is just is the secant. And then the even and odd identities, sine of minus u is which? Sine is an odd function. Think of it as graph. So the sine of the negative is the negative of the sine. Right? If you go this way, you're going, sine goes like this. So you go a little bit this way, you get the negative if you go a little bit of this way. It's the opposite of it. Okay? But cosine, and cosecant, because it's reciprocal, is also negative cosecant. I never use that one, but it's true. Okay? Cosine of minus u, though, is cosine of u, because cosine is an even function. You go a little bit this way, you get the same value if you go a little bit this way. So those are the same on either side. And secant, because it's reciprocal, is also even. Tangent of minus u would be tangent of minus u. Anybody? Opposite of tangent u. Think of how they look. Tangent does like this, right? So you go a little bit this way, you go down, the same up way, you go up, they're opposite of each other. Cosine would be the same as each other, so that would be the same, these would be opposite. Of course, cotangent would be as well. Now, the main ones we use will be these. Occasionally we'll throw in those, seldom we'll use those. They're true, they're really easy, but they're just not, I don't ever find a lot of use for them. There will be some. Will be a couple of places where we use this. So, now, let's go back. I did this before when we had these. I don't know if it's worthwhile to do it again. You can rewrite this several different ways. One way, subtract cosine squared from both sides, right? You get sine squared is equal 1 minus cosine squared, right? Or cosine squared is equal 1 minus sine squared. Or, since you had a sine squared with 1 minus cosine squared, take the square root of that and you get sine is equal to plus or minus the square root of 1 minus cosine squared. And cosine is plus or minus the square root of 1 minus sine. You can manipulate these, I want to say dozens of ways, but many ways, okay? This one, you can subtract 1 from both sides. You have tangent squared equals secant squared minus 1. It's the same identity, it's just rewriting. Or, subtract tangent squared from both sides. You have secant squared u minus tangent squared u is equal to 1. Okay? Or you could take the square root of both sides. You have secant is equal to the square root of 1 minus tangent, or 1 plus tangent squared. Or subtract 1 from both sides and then take the square. You can just do lots of different manipulations with these and have lots of different Pythagorean identities, all coming from the same ones. In fact, all coming from that right there. And this one you could take the square root of both sides of this, have cosec squared is equal to plus or minus 1 plus cotangent squared. You could subtract 1 from both sides and do the same thing here. You could subtract cotangent squared from both sides. And you can factor that then. You can just do lots of different things with those. And that's what they're talking about here. Whoa! This is one of those I just said. Sine of u plus or minus 6. Are we out of time?
It should 11:08.
Oh, we got time. Okay. I thought okay, got 2 minutes. Let's finish this slide. Okay, sine is plus or minus 1 minus 7. Or tangent is plus or minus, yeah, I showed you how to do that. Okay? Where the sine depends. Oh, what does the sine? How can you have a plus or minus there? Where in the world are you anyway? If you're in the first quadrant, this would be a plus. If u is in the second quadrant, you choose the plus. However, if u is in the third quadrant or fourth quadrant, you choose the minus. So it all depends on what the value of u is for both of those. It's just different values. For this one, you would need to be in the first and third quadrant to use the plus, second and fourth quadrant to use the minus. Okay. All right, so we'll start next time at using the fundamental identities. We didn't get any examples done, so there won't be any new homework exercises here, but we will go from there. So please, folks, try to get me at least one test or a research paper. If you haven't already gotten something turned in, get me something Thursday if you can. All right, good deal. Any questions? We'll see you Thursday then.
See you Thursday.
What's that? Oh, okay.
See you Thursday.
Okay.